Just a couple of little updates from where we were before. I think probably when we met on Monday, I was hoping that at least one of my very low enrolled classes I'd be able to cancel. Not a one. Okay, there was somebody who needed it to graduate or to, keep on track in every class. I think it was just one person in each class. So my Cal 3 class has, I think, 3 in it. Differential equations, I think, has 2. And linear algebra, I think, has 2 or maybe 3. So no new office hours have opened up, which, of course, means that grading and Blackboard and everything else is going to be a little bit slower because right now on this campus, the only office hours I have to speak of are Monday, Wednesday afternoon, 3:15 to 5:15. That's it.
The upside though, you don't have a lot of students to grade.
What's that?
You don't have a lot of students to grade.
Well, that's true, except that my class right before this, you see the extra chairs in here? Had to have them because it was packed to the gills. And my Tuesday, Thursday 8 o'clock class is almost this many. And my Tuesday, Thursday 9:30 class is probably 17 or 18. And then my physical science class is like 25 or something like that. So I have 4 very healthy classes. And then second mini term I have even larger physical science, but that's not at the same time. And then I have these little ones. But I don't mind. I enjoy teaching. I love calculus, and I like teaching. So it's just that I'm not going to have any office hours. Second mini term, because my physical science class starts 2 hours later, then I will have 2 hours then that I don't have now. So that will get a little bit better then. The other thing is this week being the first week of class drop add, we're going to be canceling some classes, and because I'm the department chair, that falls on me to do. But before I cancel a class, I always try to call the students and see if I can help them rearrange their schedule before we cancel the class out from under them. And so I got 2 done yesterday, and Monday, and I'm going to be working on others of them today. So bad news, and therefore I'm not going to be able to start working on Blackboard stuff until I get those done. Once I get those done, then I'll start working on Blackboard. So it may be the weekend before I get it done, but hopefully I'll get it done soon. All right. Enough of my sad song, okay. They like to have these little pictures and things that are supposed to make you think, oh, I want to learn this because this makes so much sense. Okay, so I hope you're saying that right now, aren't you? Please? Okay, now. This is not the one that's in your book. In your book, which you don't have, is carbon dating. That's on match.com. No, I'm just kidding. Check it out. Which relies on exponents and things that we'll be covering in this chapter. Here is a field with a windy road through it. Why they put the road like that, I'm not sure. That sure wasn't the best way to do it, it looks like, but they did. But integration solves the ancient mathematical problem finding the area of an irregular region. And that's certainly an irregular region. And farmers like to know what area they have in the field, how much seed they have, how much fertilizer, that kind of stuff. So this is just, oh yeah, I can see, I want to learn to do integration. Okay, I know you're thinking of that right now. All right, let's go to a couple of things that hopefully you already know. You went to Atlanta for a soccer tournament, right?
Yes, sir.
Okay. I wonder if you thought, if I drive, of course you would drive 60 miles an hour, wouldn't you? Or a little more, maybe. And if I drive that fast, how long is it going to take me to get 150 miles there or whatever? You do this in your head all the time almost, don't you? Distance traveled is velocity, miles per hour, times how many hours you drive. That gives you how many miles you travel, right? Yeah. Okay? So there's a very typical kind of formula. Distance is equal to V times the time elapsed. Usually elapsed time we call delta T. Difference between start time and finish time. Actually finish minus start. Delta means difference, right? Difference is subtraction. Okay. So there is a formula you use in everyday life. Now, why are we talking about that now? Well, if you had a graph and you had time on the horizontal axis and velocity on the vertical axis, and your velocity was a curve of some nature, because you don't always drive at the same speed, you don't always get to cruise control, then your distance travel would be the speed times time, speed times time, speed times time, on like that. It's the area under that curve. Does that make sense?
Yeah.
Okay, so that's what we have here. The distance traveled would be the area under the graph of velocity over some time interval t1 to t0. So typically we put the independent variable on the horizontal axis at almost always time, sometimes x, sometimes other things, the independent variable. The dependent variable, velocity, would be on the vertical axis, and then your distance travel would be the area under that graph. Now the graph may be a nice smooth curve. It could be a straight line if you're on cruise control, right? It could be something like this if you're stopping at stop signs and stoplights and stuff for time intervals, But still, whatever it is, the distance is the area under that graph of your velocity. Okay? Now, where in the world is this slide? See, these slides are from the old edition, because the new edition, oh, there it is. This is on the next page here. Before we get there, let's go back and do this. Now, yeah. All right. I don't see figure. Okay, there it is. If you're on cruise control, it's constant. I wish they had this figure. I will basically draw it for you. If you were going, oops, wait a minute. I like to get a darker pen. I forgot to do that. Okay. If this is the time axis and this is the velocity axis, okay, and you're going from t1 time to t2 time, and you're going at a fixed rate of speed, v, whatever that is, okay, that doesn't look fixed, but let's say it is, over that time interval, the distance travel would be the area under that curve. Constant speed times the time interval, t2 minus t1, that would be how far you travel. It's not obvious that is, but yeah.
So from T1 to T2 is like 10 miles?
No, that's time.
Oh.
Those are times. From 30 minutes to 47 minutes. You're traveling at a constant rate of speed. Or 1 hour to 15 hours, constant rate of speed. Whatever it is. But if you're traveling at constant rate of speed during that time, that's how far you travel. The area under there is how far you travel. Now, let's clear that one. And let's show another one. Figure 2 shows that from 0 to 2 minutes, you traveled at 10, let's see, what is it, 10 what? Meters per second. Okay? And then from 2 to 3 minutes, you traveled at 15 meters per second. Okay? And from 3 to 6 minutes, you traveled at 30. No, I'm sorry. Yeah. I'm sorry, I said it wrong. I was reading their numbers and let me start over. Okay, sorry about that. What they wrote was not what I was understanding it to be. All right, let's start with a scale here. They didn't put a scale. Well, they did. I just didn't see it. 5, 10, 15. Okay, there's a vertical scale. From 0 to 2 minutes, you traveled at 5 meters per second. Okay. From 2 to 3 minutes, you traveled at 15 meters per second. And from 3 to 6, you traveled at 10 meters per second. And from 6 to 8, you traveled, and these are in seconds. T is in seconds, and velocity is in meters per second. Okay? You traveled again at 5 meters per second. Okay. Now, obviously, my scale isn't quite even. How far did you go in that time?
So 65 meters?
65 meters, is that what you said? You're absolutely right. This was 10 meters you traveled in that first 2 seconds, 15 meters you traveled in the next second, 30 meters you traveled in the next 3 seconds, and another 10 meters you traveled in the next 2 seconds, and that's what you're adding together. 30, 40, 50, 65, yeah, 65 meters. You're absolutely right, okay? No calculus involved, right? No, okay. Now, what if, I wish, let me see. Oh, there. They have the slides in such weird order. That's that first one that I did. If you're travel constant velocity over some time interval, then your area, your distance travel would be the area v times delta t, which is t2 minus t1, which is what we just did. And then here's the one we just did. I wasted all that time drawing. Now they put it in. Okay, they do that sometimes, get the figures completely out of order. Okay. Now, here is the next issue. What if we have a curve that we're following? Okay, that is not incremental like that, but a nice, smooth curve. And that's really how you drive, isn't it? I hope, anyway. I'm not behind you. You're stopping. And yeah. This is more typical of how you're driving. How in the world do we estimate the distance traveled then? Well, there's a couple of ways. One way is to draw a rectangle just like we did before and say, let's do the left end point. And you drive this far, you go at this speed for 1 second. This is again meters per second. And then you go that far, that speed over the next second. This speed over, and why they did 2 seconds, I'm not sure, but they did. And then they did this speed for the next second, and this speed for the next 2 seconds, and that. So there's an estimate. You think that's how far you really traveled? No. You've underestimated, right? Okay. How can you make that estimate better? later. Yes, but very nice. If this was a parametric equation, yeah, you would actually do it by arc length. But we aren't anywhere close to that yet. So one thing would be, well, why did we take the left endpoint? We could have done the right endpoint. So I can't, if you recall, I can't write on that one. So what if we did the right endpoint and we did these as our estimates? That would be the same. Okay. Okay. Now that one we overestimated, right? The first one we underestimated, this one we overestimated. Why not take an average of those two? That would be better, wouldn't it? But still not probably exact. Okay? In fact, nowhere, well, closer to exact than this is, but still nowhere close. I mean, not there. Well, what if we did, say, the midpoint rather than the end point? That one, that one, that one, that one, and that one, okay? That might be a little better, but it's probably not much better than the average because it looks like that almost is the average between the two. You can get a little better by trying some of these things, but here's what really gets you better. Let's use smaller increments. Rather than doing 2 seconds here, let's just do 1. Whichever one you did, you could get a better one, okay? And then what you could do is make a smaller increment, maybe half a second. So this would be, say the first one would be here, and then the next one would be, let's see, the first one would be here, the next one would be there. So now you have a smaller error, okay? Before the error was all this white in here, now you have just that part error. And this part, that part. And so you make your error smaller. And then what we do is just keep getting smaller and smaller and smaller increment until your delta t becomes a dt, just like we did in derivatives, right? And then you would have it, okay? I'm jumping way ahead there. So let's go back and let's look at how they did the points on here, okay? What you're going to do is pick your, now we were doing t's, now it's doing x's. I don't know why they changed to that. But the first endpoint's A, and the last endpoint, let's say is B, but something out there, okay? And we have increment of delta x, okay? And delta x would be how far between. So if you have n of these, here's 1 delta x, 2 delta x, 3 delta x, 4, until you get n minus 1 delta x to n delta x. So you have a total of n increments, okay? Your total length there is b minus a, right? B is that n, a is this n, divided by n, that's how big your delta x is, okay? So the first one would be a plus 1 delta x, then a plus 1 delta x plus another delta x would be a plus 2 delta x, a plus 3 delta x, a plus n minus 1 delta x, a plus n delta x. That gets you to b, because that's how we define it. So these are your intervals. Now this is a very regular partitioning. Each increment is the same length, delta x, unlike 2 seconds and 1 second and 3 seconds like we were doing before. So, where does this lead? Well, here's what we want. We're wanting the total area under this curve. okay? Here's your A, here's your B, and here our N was 1, 2, 3, 4, 5. So N is 5, so B minus A divided by 5, that would be your delta X. Whatever that length is divided by 5, this would be, your delta X, okay? And every one of this would be A here, A plus 1 delta X, A plus 2 delta X, A plus 3 delta X, A plus 4 delta X, A plus 5 delta X. You divided the interval A to B into n subintervals, each of with delta X, okay? Now, what you want is the area under the whole curve. We don't have a way to do that yet, but our best guess, and here they did right-hand endpoints here. Let's do that curve. Let's go up here and do this and estimate that by a rectangle like this. Well, that overestimates a little, underestimates a little more, okay? And then this is your second endpoint, and that underestimates here, overestimates just a little bit. So you're still underestimating. This one, though, underestimates the whole time. Overestimates the whole time. That one does pretty much too. This one underestimates. So, yeah, it's not going to be bad, but it's probably not going to be great. Okay? How do we make it better? Decrease the interval size. Make our delta X smaller. Let's divide rather than n by 2n. So now we have one here, and that one will be much less error. This will be much less error. You do this one, and that would be less error. This would be quite a bit less. Let's do this one, and you get less of an error there. This one, less of an error. So every time you divide, make a smaller delta X, you get a better estimate. Okay? But that's constructed with right-hand, what they call endpoints. Okay? Now, these sums have a name. Okay? And they haven't given you that name yet. We will get it soon, but they're calling it R now. And I can easily imagine you say, why do you call it R? Okay? These are called Riemann sums. And in just a couple pages, you'll see a picture of Riemann. Okay? So that's why it is. No, I'm sorry. Wrong. This is called R because it's a right hand. Sorry. This is R because it's right hand. You've divided that interval from A to B into n divisions, and you're going to use the right-hand one of each of those. So that's why it's capital R. Okay? So, let's go back here and see what we do to estimate the area of this one. Okay, I'll blow it up again. Boom, I blew it up. Okay. Now, you do f of, this is your function f, right, of a plus delta x, that's that point right there, times your delta x. And right here, this is a plus 2 delta x, that's the x value here, a plus delta x, that's 2 delta x. So that's this one, and that's the area of that is f of a plus 2 delta x times delta x. And this will be 3, that will be 4. Every one of those is multiplied by delta x. So you can factor out the delta x, and what do we have then? The sum of f of a plus delta x plus f of a plus 2 delta x plus f of a plus 3 delta x plus f of a plus 4 delta x plus f of a plus 5 delta x. That is your right-hand sum, and that's what we have here. Okay?
So it's n the b basically?
N is the number of intervals you have. In that example, it was 5. It may be 4 million. It may, whatever it is, that's how many increments you have. And you know that ahead of time. So, R sub n, give me an n, make up one. 8. So that would be delta x, because all those delta x's were the same, times in the right hand of that alpha of a plus 1 delta x plus alpha of a plus 2 delta x plus alpha of a plus 3 delta x, 4 delta x, 5 delta x, 6 delta x, 7 delta x, and you get 8. You chose 8, and that would be 8 numbers of those added together multiplied by delta x. Right?
Yeah.
Okay. So n is whatever number you choose for the number of increments. And you evaluate the function at each of those right-hand points. Okay. Now, I wish we'd minimize this. Remember in Cal 1, when you had to do all those limit things and all like that, and it was sort of gaggy? But then after a while, you were really doing derivatives, and who cares about those things anymore? Okay. This is the gaggy part. Okay, I'm sorry. Did I say that? Okay. Now, here's a function. It's your good old quadratic function. Now, it doesn't look like a quadratic function. That's because this is 1 unit here, 1, 1, okay, and this is 5 units here, okay. So this is really squished. You've expanded the x-axis and compressed the y-axis. So this is your parabola. Alpha of x is equal to x squared. And we want to approximate the area under here by the right-hand values, okay, when you have 4 increments. You're doing from 1 to 3 with 4 increments. So what do? We do 3 minus 1 is 2 divided by 4, and that gives us 2 divided by 4 is 1 half. So therefore each increment is 1 half. And this will be 1 plus 1 half, which is 3 halves, 1 plus 2 times 1 half, which is 2, 1 plus 3 times 1 half, so that would be 2 halves plus 3 halves is 5 halves, and 2 halves plus 6 halves, 4 halves is 2, that would be 1 plus 2 is 3. So yeah, there's our values here. We calculate alpha of 3 halves, 2, 5 halves, and 3. Well, alpha of 3 halves is square this.
Would be 9
9
fourths.
fourths plus
2.
no, square it,
4.
plus
25 fourths.
yeah. Okay, I'm going to start writing these down. That would be, I can't write it there, sorry. Okay, here, this will be, alpha of this would be 9 fourths plus 4 plus 25 fourths plus 9, okay? That would be 13 plus 34 fourths, right? I'm sorry? Okay. I'm adding these things together. 9 plus 4 is 13. 9 fourths plus 25 fourths is 34 fourths. Okay. So that's the sum of those. Our interval is 1 half. So let's figure what this is. This is 13 plus 17 halves, right? This will be 26 halves plus 17 halves, right? Okay, and that will be 43 halves, right? Okay, and then multiply that by the delta x, which is 1 half, so that will be 43 fourths. So that's approximately 1, 0, and 3 fourths, right? 10 and 3 fourths. Yay or nay?
Yeah.
Okay. All right. Well, let's do a smaller increment. Let's now this time do R6. Again, we're going to use the right hand, but we're going to do 6. So what we do, since we're going to n is 6, we still have 2 here. 2 divided by 6 is 1/3. Okay? So we'll have 1 and 1 and 1/3, which is 4/3, 5/3, 6/3, which is 2, 7/3, 8/3, and 9/3, which is 3. Okay, those will be the values. Those are what we're going to calculate there. So we got to do those. 4/3 squared is 16 ninths plus 25 ninths plus 4 plus 49 ninths plus 64 ninths plus 9. Okay? Yeah, we got to add these in. Well, there's my 13. I can do that one. Okay. Now let's do these. 25 plus 49 is 74, right? Okay. And 16 plus 64 is 80, right? So 74 plus 80 is 154 ninths, right? Okay. I can't simplify that any, can I? Yet. Okay, so this will be 9 times 13 would be 27, 57 ninths. Is that right? No, that's not right. Brain's not working well. 13. It's, the 7 part's right. 9. 117. Is that right? 13 is 117 ninths. Okay. Plus 154 ninths would be 271 ninths. Is that right? And multiply that by, what is your delta x here? 1/3. Okay. So that makes this a 27, right? Oh, I see what that is. That's 1, 0, and 1 27ths. 10 and 1 27th. Before we had 10 and 3/4. Okay? And I'm guessing this is a bigger error here than what you have there, because these are each smaller than those, right? Yes. And with them. Okay. Now,
It's getting closer to 10.
huh? Pretty close to 10. Now, I'm going to cheat. Is that okay? Okay. We're going actually, and you don't know how to do this yet, so don't get carried away here, but we're going to integrate, okay, from 1 to 3 x squared dx. Okay. The f of x was your x squared, right? And your dx, that was your delta x. So we're summing all those together. Now, you don't know how to do this yet, but I'll show you how to do it. Okay, we're doing an antiderivative. Remember how we did an antiderivative?
Yes.
I know it was 2 days ago, yeah.
So it would be x
X cubed
over 2.
over 3.
Oh, yeah.
Remember, you go up by 1. You have derivatives, you go down by 1. Integration, you go up by 1. Antiderivative, you go up by 1. And then divide by that. And we're going to evaluate that from 1 to 3. Okay? So that means we'll do 3 cubed, which is 27 over 3, minus 1 over 3. And this would be 9 minus 1/3, which is going to be 8 1/3. 8 2/3. That's exactly. So it wasn't all that close to 10. it was decreasing, it was going to keep decreasing until you got down to 8 2/3. Wow.
It's easy.
That's so much easier, isn't it?
Yeah.
It's like doing limits of alpha of x plus a minus alpha of x divided by a, right? You just do an antiderivative and plug it in. You're not supposed to know how to do that yet, okay? And they didn't tell you what the real answer was, but that's what you get, okay? Now, next thing we're going to talk about is this summation notation. Have you run into this before? What we were doing was adding a bunch of things together, right? Here's a short way of doing this, okay? The summation, that's a capital Greek letter sigma, okay? Meaning you sum from j is equal to m to n, okay? Of a sub j, okay? That's sort of what we were doing before, okay? And what that means, you start with j equal m, so that'd be a sub m plus a sub m plus 1 plus a sub m plus 2 plus dot 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 up to plus a sub m, let's see, let's call this n minus 2 plus a sub n minus 1 plus a sub n. We go all the way up to n, okay? You just do each one of them, okay? So give me an m. 5. Give me an n. 10, okay? So a sub j, when j goes from 5 to 10, will be a sub 5 plus a plus 6, so a plus a sub 7 plus a sub 8 plus a sub 9 plus a sub 10. That's just adding all those a's together, whatever they're standing for. That's called summation notation. It just makes it shorter to do, okay? But you know you don't have to just have a letter in there. You could have the number, the counter itself. If j is going from 1 to 5, say, and you did of j squared, what would that be? Starting at 1, 1 squared, 2 squared, 3 squared, plus 4 squared, plus 5 squared. And you could see it? You did it in pre-cal? Okay, yeah. So this would be 1 plus 4 plus 9 plus 16 plus 25, right? That would be 10, that would be 20, that would be 30, this would be 55. I really like to cheat and find the easiest way I can do these things. Is that okay? Okay. Now, you could have said that was a sub j, but a sub j equal j squared. So j squared is called the general term. And the letter j is called the summation index. Whatever you're counting from, that's the summation index. And sometimes it's called the dummy variable, if we want to be insulting to it. Oh, no, I'm sorry. Okay, a dummy variable. Because any other letter could be used. That could have been an I, it could have been a P, it could have been anything. It has no meaning in itself. It's just what we're using to represent it. So let's do a few more of these. Let's do the summation from k equal 4 to 6, okay, of k squared minus 2k. What do you think that would be? 4 squared. 8 plus 5 5 squared,
minus
10, 6 squared,
12.
minus 12. And that's it, right? Well, this will be 16 minus 8 plus 25 minus 10 plus 36 minus 12. Okay. Is there anything we can do? Okay, I see these minuses. These two minuses add to minus 20. That will be a minus 30. And let's see what our pluses do. These two add to be 52 plus 25 is 77. So 77 minus 30 would be 47. I'm doing it. Ah, yes, that's right. Right? Okay. However you do it, that's what you wind up with. Okay? Now, how about this one? This is a really hard one, so put your thinking cap on. Okay? What is the summation from m equals 7 to 9 of 1?
Equals 1.
Huh? It's just equal to 1?
Yeah.
Wait, when m is equal to 7, that would be 1 plus, when m is equal to 8, that's still 1 plus, when m is equal to 9, that's still 1, 3. Okay. High level math. Okay. All right. Because all the values are 1. No matter what your I is or m is, the value is 1. So here are some of the, that's right, I was supposed to not be doing all this, so I thought we were supposed to be just doing the slideshow. But this isn't hurting, is it? Or are you okay with it? If this is too simple, we can go faster. But here is the linearity of summations. Okay? If you had the summation of j equal m to n, whatever values those are, of a sub j plus b sub j, you could just do am plus bm plus am plus 1 plus bm plus 1 plus am plus 2 plus bm until you get up to a sub n plus b sub n. But what you could do, the summation of a sum is the sum of the summations. Okay? So you can break it up if you want to. The sum of, since those things are all being counted the same, just sort of like bring the summation inside that, right? Or if you have that same summation, but now c times a sub j, well, what you can do, since this c is just a constant, it doesn't depend on j, pull it on the outside and do the summation from j equal m to n of a sub j. And that will work too. Okay? Now, what if you're summing j equal 1 to n, but you're just summing k, like before we just did 1. So that would be k plus k plus k plus k when you go from 1 to n. So that would be n times k, right? Because k is common to all of them, and you're doing that n times, so it would be n times k. For k is any constant as long as n is greater than or equal to 1. Here's what we assume always. This number is greater than or equal to that number. You most of the time don't want the n to be less than m. Otherwise you're counting backwards or something, and I don't know exactly how to do that. Okay? So
We just like subtract instead of add.
kinda, yeah. Yeah. Okay. So that's right. I had meant to go through this faster. So let's do that now. So let's go back to our r sub n's. Remember that right-hand values. Then how we write that in summation notation would be this. R sub n, remember the delta x times all of them. So the delta x times your summation of j equal 1 to n. Remember you're doing 1 to n, that you have in increments. Okay? 1 to n of f of a plus j times delta x. Because remember a times a plus delta x plus that f of a plus 2 delta x plus f of a plus 3. Yeah, that's it. So this is how we write what took up a whole line before in summation notation, right? Those are your right-hand sums. Okay. Now, we could have done left-hand sums as well, okay? The only difference would have been that then, if you're doing the left-hand sum, but you're doing the same thing, here's your a plus delta x, a plus 2 delta x, equals 3, up to a plus n delta x. But if you're doing the left-hand sum, now you're starting at the 0 here, just f of a, plus 0 delta x. Then the next one, the second one's going to be f of a plus just 1 delta x. So now we just move the counter down to 0, but don't go to n, go to n minus 1. And that gives you your left-hand sums, right? Okay. So it looks almost the same, you just change your counter, drop it by 1 on both bottom and top. Okay? Now, what if we're using the midpoint? I mentioned the midpoint, we didn't say how to do it, but here's what it would be. Okay? The midpoint between, say, j equal 1 to j equal 2 would be 1.5, wouldn't it? If you have the curve here, and here you have your a plus delta x, a plus 2 delta x, a plus 3 delta x, like this. If you're doing the midpoint, that would be a plus 1/2 delta x, right? Next one would be plus 3/2 delta x, plus 5/2 delta x. So what you do for the midpoint is delta x times them all, times the sum of now your j is going from 1 to n, f of a plus, and it's j, that would be 1 minus 1/2, because you always drop back a half to get that half. You could have done j equals 0, and that is j plus 1/2. That would be fine too, but then you would go to n minus 1. If you're doing j equal 1 to n, then you subtract 1/2 from it. And that's what your value would be. And remember, I suggested the midpoint rule, midpoint one would probably give you a little more precision most of the time than the right or left. But who cares really? I mean, they all do. Okay? Now, seems like they should have done midpoint when they did left and right. Well, actually, they didn't really do left very well. They just showed you right and then threw in the left to midpoint. So here would be the left-hand rectangle for this curve. I think the same curve we had before. We use this value for this rectangle, this one for this rectangle, this one for that one, this one for that one, and this one for that one. So this underestimates, overestimates, underestimates, underestimates, overestimates. The midpoint rule, you do j equal 1 minus 1/2. So that would give you this as a value. Do your rectangle there. And notice it's a lot less error than what you had here. Midpoint here would be some under, some over, not much over. This one a whole bunch over. That's a much better estimation. This midpoint a little under, almost the same over. That's going to be almost the same. This was all under. Okay, so yeah, that's a lot less error. That one a little over, a little less under, but this is all under by a big shot, by a big amount. And then that last one is a little over, under, a little over, and this is all under. So that's going to be a far better estimate there, right? But it's a pretty complicated looking formula, with those halves in there and stuff. But it's still pretty simple, relatively simple. Okay. Now this is the figure for example 2, and we weren't going to do example 2. I'm sorry, I got carried away and started really doing it. If here's your curve, and you have the left-hand endpoint L6, and this is, they don't tell you what curve it is. Oh yeah, there it is. F of x is equal 1 over x, or x to the minus 1. this scale and probably shorten that scale. No, I don't know. They just don't have it scaled well, but that's okay. This is what it's looking like. Well, they did it so you can see this better. Okay. The left hand input is going to be this and this and this and this and this and that. The right hand input is going to be this and this and this and this and this and that. Okay. Your midpoint would have been this and that, 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 that. Okay. They didn't show the midpoint here. The left hand input is always overestimating. The right hand endpoint is always underestimating when it's a strictly decreasing function. That sort of makes sense. If you go back before, this is increasing, decreasing, your midpoint is varies with that, you know, but there was an increasing function, and here, they didn't show it, but your right-hand inputs are overestimating, and your left-hand inputs would have been underestimated, right? So, depends on whether increasing or decreasing, which one of them is over and which is under. But we sort of probably would have guessed that. Sure you would have, right? Okay. Now, there's a midpoint on that same one. Okay, here's your left is the white, the tan is the right. Here's your midpoint. Better than either one by pretty much a long shot, right? Okay, just like we noticed before. Okay. Now, this leads to this little blurb about monotonic functions, and that's what this one is doing. Monotonic, what does mono mean? One, very good, okay? And basic, it means one direction. A monotonic function is either strictly increasing or strictly decreasing, only going in one direction, okay? This is not monotonic. This is not monotonic. That probably isn't either. I can't remember if they allow for equal. I don't think they do. I think it always has to be increasing or decreasing. Okay. But moving on, computing area as a limit of approximations. Okay. I don't think I can get all this on one, but let's see what I can. Oh, yes, I can. Look at that. All right. Here we're estimating the area under this curve from A to B. And since this is an increasing function, the right-hand endpoint is going to overestimate big time. Left-hand endpoint would have underestimated big time. Midpoint would have been better than either of those, but still probably not right on the money. Okay? But you see, this is our error on the R. We're doing R2 here. When we went up to R4, okay, notice this one here was our error here. Now you decrease this part to just that. Really a huge decrease. This part stayed the same. That's okay. This part is a huge decrease, and that part stayed the same. So you've decreased your error by the sum of those two dotted rectangles, right? Much better. If you decrease that, double that again, make it 8, then basically you're doing this one, which decreases by some. This one stays exactly the same. This would decrease by a good amount, and that next part would stay the same. This one would decrease that. So it's probably not as big a decrease as this, but still a pretty good decrease. So you see, the larger your n is, in other words, the smaller your delta x is, the more precise you're getting on your estimate. Still not there, but you're getting better every time you do that. Okay? So the error decreases as you increase the number of rectangles, which is decreasing your delta x. Okay? Now, here is the first theorem. And that's one reason I sort of like to go on and do a few problems, because this is really boring just talking about them, but we need to move on. If f of x is continuous on A to B, what does continuous mean?
It's a smooth curve.
Okay, it doesn't have to be smooth, but you got the right concept there. The curve doesn't have any breaks in it. Smooth would mean it doesn't have any points in it, okay? That's a continuous function, it's just not smooth. But, so continuous means there are no places where you jump in values or have holes or things like that. So if alpha is a continuous function on A to B, then the endpoint and the midpoint approximations approach one and the same limit as n approaches infinity. In other words, there is a value L, limit, such that the limit as n approaches infinity of r sub n is the same as the limit as n approaches infinity of L sub n, which is the same as the limit as n approaches infinity of m sub n, which is midpoint 1, and that limit is going to be what we call L. If f of x is always a greater than 0, then we define the area under the graph from A to B of that f of x, a continuous function, to be that limit L. If you got smaller and smaller and smaller increments, then that would be the area under the curve. So here we are back down to limits again. Aren't they fun? Okay. Now, here are our power sums. They're going to do a new superhero movie about power sums. Somehow I don't think it'll fly. Okay. If you do the summation of j, when j is going from 1 to n, remember that to be 1 plus 2 plus 3 plus 4 up to n. Okay? Now, if I told you to sum up all the integers from 1 to 100, could you do that? I'm sorry?
Said if I had a calculator.
If you had a calculator. I suggest to you you could do it without a calculator. You wouldn't like it, would you? But you could do it. Okay? Can I jump back and just say 1 to 10? Okay. So, okay. Now you could do that, couldn't you? But you still wouldn't like it, would you? But what if we did this? Huh? They all add to 11, and how many do we have? 5, so it'd be 55. Did you use a calculator? Okay. I think that was faster than using a calculator, wasn't it? Yeah. Okay. Well, guess what? If we were to sum j going from 1 to n, no matter how big n was, what we could do would be, okay, now let's get it, okay? n is, and this problem right here was 10, and n plus 1 is 11, right? And 10 times 11 was 110 divided by 2.
Be 55.
Yeah, which is what we got. Okay. Now, I think the way we did it was actually easier and simpler than that, but basically, if you think about what we just did, n plus 1 was 11, and we did half of n, half of 10 was 5, right? We did half of it. So yeah, that's exactly what we did. 11 times 5 is 55, right? Now, if you multiply this out, that's n squared plus n divided by 2, which is n squared over 2 plus n over 2. There's a general formula, no matter how big or how small or whatever n is, either one of those always works. Okay? Now, the others aren't nearly as easy, but here just happen to be a few of them. The summation, I'm going to blow this up so we can see it. I wish I knew some quick ways to show you this and commit you. They're pretty simple, but here's what it is. The summation of j squared, which of course, j going from 1 to n, it would be 1 squared plus 2 squared plus 3 squared plus 4 up to n squared. Okay? Well, no real easy way, but this just happens to be, these are just some of your power sums. N times n plus 1. Hey, that's looking similar, isn't it? But the next one is 2n plus 1. But now it's divided by 6. Okay? Interesting. Which would be n times n times 2n would be 2n cubed divided by 6 would be n cubed over 3 plus, this one will take a little more effort, n times 1, that would be n squared, plus n times 1 times 2n, that would be 2n squared, so it would be 3n squared divided by 6, which is n squared divided by 2, and then finally got n divided by 6. Okay. Okay. Let's go to 3. J cubed. Well, what I was going to suggest might have worked before, I'm not sure will work anymore. Except that voila, it says n squared times n plus 1 squared divided by 4. Which would be, if you again multiply these out, n fourth divided by 4 plus n cubed, this would be n squared. Okay, if you did this one, that'd be n squared plus n plus 1, plus 2n plus 1, right? Okay, so then n squared times 2n would be 2n cubed divided by 4 would be n cubed over squared over 2, and then this would be n squared over 4. So, this is all well and good, but I'm trying to think when we'll ever use these. Okay? I'll tell you now. When you get to Cal 2 and you do infinite series, some of these will be becoming useful. Remember these then. Not memorize them. Remember where to go look them up. Okay? Go back to this section to do that. I don't know why they put that in there because, frankly, I don't see that much practical need for it. Okay? So let's move on. Now, This is a figure illustrating something we've already talked about somewhat ad nauseum, okay? Remember when we said if you increase the n, you decrease your error. Or decrease your delta x, you decrease your error. Here you had 0 to 4, n is equal to, delta x is equal to 1, or n is equal to 4. There's your errors. When you do 8, that's R8. R4, there's R8. You decrease the error big time. When you do R16, take half of these every time, you decrease it even more. So the right-hand endpoints, okay, if you kept going to n equal infinity, then you would have that. The right-hand endpoint approximation approached the area of the triangle. This one was getting, when you get from here to here, you got closer to that. You got here to here, you get closer to that. Keep going smaller and smaller. Ultimately, you're going to get there. That's your limit. Okay. Now we know what that one is. That's 1/2 length times width, base times height, which is 4 times 4 is 16. Half of that is 8. We know that's going to 8. You could go back and calculate all these if you wanted to. I don't. Okay. And you'll see you're always overshooting, but every time you're getting closer and closer to 8. Okay. Did you say something? Oh, was that in the hall? Okay. Sorry. Okay. This is a formula you'll see on, oh, you don't have your book. Page 266, I'll say it, so in case you do have a book to look at. What was the deal? Were you going to get an e-book? Is that what it was?
Yes, sir. I'll put it on my laptop.
Yeah, okay. And you left your pencil and your laptop at home, huh? Okay, no, just kidding. Okay. All right. This must be some problem.
Just take the left-hand side.
What's that?
Just taking the left-hand side.
Yeah, it's the left-hand side, but what is the problem here? Okay. This is that same one that we were doing.
I don't see the point of it.
Yeah, if you think about it, this is showing that that limit really is 8. As n goes larger and larger and larger, this is going to 8 minus 8 over n. As they get larger and larger and larger, this is getting closer and closer to zeros. That's what it's showing you. I just can't right now figure out where they got that 16 over n squared. I'm sure it's pretty straightforward, but I
Would the 16 over n squared be the constant?
that's what I was wondering, is that your delta x? But I don't see why it would be delta x, because delta x would be 4 divided by n. That would be delta x squared. So I'll leave it alone, because, okay. This is just a figure that they're going to use for example 4, which we're not doing. they're using those, and remember those power sums? They're using those like crazy, okay? And it's fine, it's perfectly reasonable to do, except why go through all this struggle when you'll never use it again?
It's the same thing as getting an engineering degree.
What's that?
It's the same thing as getting an engineering degree. You won't really use everything you learn.
Right. So I hate to do this, but I am going to do it. Okay? I don't hate to do it. I really enjoy doing it. What we're doing, and this is jumping way ahead. What you're trying to do is integrate this function 2x squared minus x plus 3 over the interval from 2 to 4. Okay? And all you need is a dx in there. Okay? Now, this is a couple of jumps here, but remember your linearity rules? You can say this is the same as 2 times the integral from 2 to 4 times x squared minus the integral from 2 to 4 x, oh, this is dx plus the integral from 2 to 4, well, let's do 3 dx. Okay? Do you buy that? Think, the linearity rules for sums, an integral is just a sum. It's an infinite sum. So basically, you can pull the 2 on the outside and just do that integral. Pull the minus on the outside and do that integral. Then pull plus 3 on the outside and do that integral. Okay? Now, what's the antiderivative of x squared?
X cubed over 3.
Perfect. Evaluate that from 2 to 4. Minus, what's the integral of antiderivative of x?
2 squared over 2.
X squared over 2. Evaluated from 2 to 4. Plus 3 times, now what's the antiderivative of 1? X. Very good. Evaluated from 2 to 4. Okay, so this will be 2 times,
4x.
no,
4 cubed.
4 cubed is?
We have 54?
64. Is that what you said?
Yeah.
Okay, I thought you did. Okay. 64 over 3 minus 8 over 3 minus 8 minus
4
over 2.
over 2.
2 squared over 2. Right?
Wait,
2.
Yeah.
Right. Okay. Is that what you meant?
Yeah.
You see it? I'm just kidding. I mean, I want you to see it.
Yeah, I see it.
Huh?
Yeah, I see it.
Okay. All right. Plus 3 times 4 minus 2. All right. So what would this be? 2 times 64 minus 8 would be
56.
56. Is that what you said? Okay. Thirds minus 6 plus 6. I can do that part. okay? And that will give you 112 thirds, which would be approximately 37 and a third. Not that they're going to change that, but just get a general idea. Okay. Let's see what they got. 112 thirds. Good for them. Right?
Yeah.
I don't care for doing all those other things. I know you want to, but give it up, Jack. Okay. Now, here is part of what they went through to get there. Yuck, okay? To me, this is busy work, okay?
I like a straight to the point.
Yeah, okay. We're on the same page. Okay, let's move to this one. Prove that for all b's greater than 0, the area A under the graph of alpha of x equal x squared, which is what we've got there. I'll blow it up so you can see it better maybe. But if I write on it, I have to unblow it up. Over 0 to b is equal to b cubed over 3. All right. So they are doing all those little pieces from all those little power sums and come up with b cubed over 3, which is exactly what we got when we integrate x squared dx from 0 to b. What would that be? X cubed over 3 evaluated from 0 to b, and that would be that's exactly what they got. The area under there is b cubed over 3. Okay? It's just saying this is what you get when you do it. And now, that works really good for polynomials. Okay? But guess what? What if you get into sine functions and other things like this? How are you going to use those power rules for your sums? You're not. Okay? What you wind up doing is doing your, I like the way they say this. The area under the graph of any polynomial can be calculated using the power sum formulas, as in the examples. For other functions, the limit defining the area may be difficult or impossible to evaluate directly. Consider f of x equals sine x. That's not a polynomial. You can't use those things. Over the integral from pi fourths to 3/4 pi. In this case, your delta x is 3/4 pi minus pi fourths divided by n. So it's pi over 2n. So that would be 2/4 pi over n, which would be 1/2 pi over n, which is pi over 2n. And the area A is, and they give you a formula, sine of pi fourths plus pi j over 2n. And I like that next little phrase, with some work. I'll interpret that for you. With a lot of work, okay, you can show that's equal to the square root of 2. Let's not say we did. Okay. Now, here you run into oh, and there it is. Okay, I'm sorry, I was doing all that. Here is your, this is what they were talking about. There's your f of x is sine x. You're evaluating that. That area is more difficult to compute as the limit of endpoint approximations. That is quite an understatement. More difficult in spades, okay? Much more difficult, okay? But, clever student that you are, you could say this is the same as the integral from pi fourths to 3/4 pi of sine x dx. Couldn't you say that? Now, what do you think the antiderivative of sine x is? In other words, what function, when you take a derivative of it, would you get sine x?
The derivative of sine x is negative cosine x, right?
Now, the derivative of sine x is cosine x.
Oh, cosine x.
But what would be the next thing out of your mouth then? Derivative of... Wait.
Huh?
If derivative of sine x is cosine x, say the next one. Derivative of cosine x is?
Sine x.
No, it isn't.
No. Negative sine
Negative sine x. Ah, well here we got a sine x. So the antiderivative of that must be negative cosine x, right?
Yeah.
Okay, so then we'd say this is minus cosine x evaluated from pi fourths to 3/4 pi. 3 pi over 4. Okay, which would be minus cosine 3 pi over 4 minus a minus, which is plus cosine of pi fourths. Now, do you happen to know what the cosine of 3/4 pi is?
So it would be well, since there's already negative, so it would be a positive square root of 2 over 2.
Okay, you got it. That would be square root of 2 over 2 plus the square root of 2 over 2, which would be 2 square root of 2 over 2, which would be square root of 2, and guess what they say the answer is? The square root of 2. With a lot less work. Remember before they said, with some work you can do, well, guess what? A lot less work you can do this way. Okay. Now, bottom of this page is historical perspective on Jacob Bernoulli. He did a lot of work with, I'm wondering if they call these infinite series yet or not, infinite sums or whatever. But if you're interested in the Bernoulli family, there was Jacob and Johann were brothers. And if I'm not mistaken, they fought like cats and dogs. They were both extremely bright, excellent mathematicians and physicists, and they probably got along okay. And then one of them, I don't remember which one, had, maybe both of them had a bunch of kids, and they were really good mathematicians. One of them was a guy named Daniel Bernoulli, and he was an excellent mathematician and physicist. And if I remember right, I may have the names wrong, but it seems like that one of these brothers, Jacob or Johann, was like top mathematician of his time, professor at some big university, and there was this competition that someone sponsored, and he thought for sure he was going to win it. So he did whatever it was to do the competition, and he found out he lost. He came in second. And guess who beat him? His son.
I'll lose to my son.
What's that?
I said I would take the second place if my son was winning.
You know what he did?
What?
He kicked the son out of the house. He said, if you're that good, you can live on your own, you know. So he wasn't nearly as magnanimous as you are, okay? That's why I said they were sort of cantankerous old dudes, you know. But I think that comes from being so bright. I don't know. Anyway, that's 5. Now you can do any of the exercises here if you want to. It's not required, but you got the general idea of what we're doing. So anyway, we're through with that one. Sorry, hit the wrong key. All right, I'll discard that, and let's go to 5.2. Oh, we only got about, what, 10 minutes? Sorry about that. I know you're looking forward to being here longer, but I've got to look.
Yeah, I think this class is longer than any of the other classes.
Yeah, because it's a 4-hour course.
It's like my physics class is a 4-hour course.
Yeah.
We were only there for an hour and 15.
Exactly, except that has a lab with it, and he'll start giving you lab stuff. But he usually does what do you call it, virtual labs. So you do those on your own. So that's why it seems a lot shorter. This is all class time, no lab time. Because we love having our class, don't we? The answer is yes. You're a good boy. You don't lie, do you? Okay. All right.
At least it's shorter than the summer class.
What's that?
At least it's shorter than the summer class.
Yeah, it is.
Summer class.
Oh boy, they were way too long. I've often wondered if I ought to make those 4 days a week, you know, the calculus, then it wouldn't be as long.
Yeah.
But would people want to come 4 days rather than 2? I don't know.
It will suck in the way as in my work schedule goes.
What's that?
It wouldn't be as good because of how my work schedule works.
Yeah.
So yeah.
So that's, you have to get one, you got to lose on the other. All right, this is 5.2. The definite integral is the title of this. Okay, in the previous section, we already had theorized, the theorem said, if f is a continuous function on an interval a to b, then the endpoint and midpoint approximations, either both right or left hand endpoint approximation and the midpoint approximations, approach some common limit as n goes to infinity. This is what we said in limits before. That L is the limit as, we got limits here, n approaches infinity of r sub n, L sub n, or m sub n. Right hand, left hand, or midpoint. Midpoint gets there quicker, but it's still, that's the same limit on all. I just have a little aversion to calling L sub n, and you think that has something to do with the L. No, that L is the left hand, this is the limit, so don't let that confuse you. You probably wouldn't have, except I said it. Okay, when f of x is always greater than or equal to 0, in other words, you don't ever dip below the x-axis, the area under the graph of f of x is that limit, okay? And then what I was trying to bring up before was the concept of Riemann sums. And this is where they bring it up. And on the next page, when you get your thing, you'll see a picture of good old Georg Friedrich Riemann, which is, I think, the German. I'm not absolutely certain, but I believe he was a German mathematician, one of the greatest mathematicians of the 19th century, and perhaps second only to his teacher, Gauss, Carl Friedrich Gauss. Riemann transformed the fields of geometry, blah, blah, blah. Albert Einstein based his general theory of relativity on Riemann's geometry. Pretty impressive. I'm pretty sure he was German. They don't say here, but I believe he was. Okay. Now, what this picture is representing is what we mean by a partition. Okay? Now, before we did A to B was B minus A divided by N, and they were all the same size. It's not absolutely required for that to be the case. If this is your x sub 0 is A, and here's your x of 1, here's your x of 2, you have a bunch more in there, and then you have x of n, I minus 1, x of I, and this is x of n minus 1, and x of n, you know, whatever, you know. They don't have to be precisely the same size, okay? That's just any partitioning of your thing and just number your intervals. Now, your sample points don't have to be right, left, or midpoint. They can be anywhere. And that's what the C1s are representing, or the C's are representing. C1, C2, C3, CI, Cn. Okay, it's always C1 is between x of 0 and x of 1, C2 between x of 1 and x of 2, C3 between x of 2 and x of 3, CI between x of I minus 1 and x of I, CI plus 1 would be between x of I and x of I plus 1, Cn between x of n minus 1 to x of n, okay? So it's always, that's how we do it. So, there. And again, nothing special, nothing fancy. You don't have to have evenly spaced intervals. I think it makes more sense to. You don't have to use right, left, or midpoint, just any value in between. Okay? So this is a bit more general than what we did before. Okay? Now, we were calling them delta x's before, but they were all the same size. Now, since they don't have to be the same size, we'll call it delta x of I, because each one of them may be a different size. Okay? So x of 1 would be whatever the first one, x of 2, whatever that one was, x of 3, whatever that one was, x of I would be whatever that one was, yeah. So x of I is the difference between, delta x of I is the difference between x of I and x of I minus 1. The difference. Delta means difference, subtraction, between the upper endpoint minus the lower endpoint. X of I minus x of I minus 1. Okay? Nothing all that crucial there, but now, this is called writing a fairly simple concept in as complicated a form as you can imagine. I'm just kidding. This is now going to be a right hand. This is where I was getting confused. This is now going to be a Riemann sum. And again, I found it awkward they used the same symbol for both. The Riemann sum of some particular function f. That same function is throughout here. We're not changing functions. It's the same function. P is your partition, however you divided those spaces. So for that partition. And C is for the set of those constants. It's not constants, it's sample points. I couldn't remember what they call them. Sample points. Okay? And they don't have to be midpoints right hand or left hand. So this is the Riemann sum of that particular function for this particular partition and that set of sample points, each one within its partition, okay? And the sum of all those would be the sum of I equal 1 to n, since you have n partitions there, not all the same length, but n partitions. Then the summation of x of I, or I equal 1 to n, of f of c I, the function at that sample point, C sub I, for each of these n things here, times delta x of I for each of those lengths of those, right? That would be f sub C1, delta x of 1, sub 1, plus f sub C2, delta x of 2, plus f sub C3, delta x sub 3, plus dot, 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 all the way up to f sub x sub Cn, delta x. Okay? That is your Riemann sum in the most general form of the function, the partition, and the sample point, set of sample points, each one being in a partition. Okay? Now, let me get this one done and we'll begin next time. We won't do sample. Goodness gracious, where did my cursor go? It must be telling me it's time to stop. You did that, didn't you? You willed it to happen. Well, I can't get it to go. Let me try it again. All right. Let's just stop.